Okay, so page 17. You guys can cross off those trig derivatives rule. Those are just references for the problems that had trig, but we haven't done trig yet, so we're just going to focus on the ones involving e to the u rule. So here's the rule that we learned last Thursday. There's a rule for e to the u, and that rule is e to the u times u prime. Let's just put it up at the top so that we can just have reference to it. It's a apostrophe there. E to the u times u prime. There's something subtle but important that I realized it was good to bring up during previous classes, is that the e to the u times u prime rule, I find that it's pretty easy because it's really just the function itself times the exponent's derivative. However, this is made and it's meant for the numerator. Okay, so this rule is meant for, or how about it's designed for a numerator term. Okay, so it's just like with power rule, right? With power rule, we always said, okay, the variable has to be up top, right? We can't do power rule if the variable is stuck in the denominator. Same thing here. This e to the u rule can only be effective if it's in the numerator. If it's not in the numerator, we have to find a way to get into the numerator before we can use that rule. Okay. So on this page, I just want us to kind of explore problems that have numerator and denominators in them, and the fact that some of the subtle differences can change the way that we can approach or look at a problem. Okay, so 47 here. We have 2 over e to the x plus e to the negative x. We want to find the derivative. To find the derivative, we can use what? I think the most obvious one is we could always use for 47. Yeah, that's what I want us to lead to. That you said chain rule. But I think if you want to do quotient rule, you can. Okay, anytime you have numerator and denominator, you can always do quotient rule. But there are times when it's maybe beneficial to avoid quotient rule, especially if there's a rule that is a little bit cleaner. So I think 47 is we could use chain rule. Okay, and what can we do? Good. Parentheses to -1. Now, something else that I want to point out is we can't just bring the e to the x and e to the negative x up to the top and it's just change those exponents from 1 to negative and 1 to positive. Okay, that plus is getting in the way. That plus is not going to make it clean for us to just move them up individually. We have to kind of move them up as a group. So that plus sign is kind of causing those two terms to kind of stick together. So if we want to bring that up, we got to bring them up as a group. And then you guys said raise to -1. Okay. So we're kind of stuck in this form, right? We can't distribute that negative through. But the reason that we feel like this is an easier, cleaner method than quotient rule is because this 2 is just going to tag along, right? There's no need for product rule. It's just going to be part of this function, right? So I prefer chain, especially if there's a numerator term that's not a variable. But we can't split it up into individual fractions because we have too many terms in the denominator. So, okay, so this is chain rule here. Let me spell out the steps here. Chain rule, there's an outside and inside portion. What's the outside portion here? 2 parentheses to the -1. And the inside portion is what you see right there. Okay, outside derivative first, y prime. Two parentheses to -1 becomes 2. So we treat the parentheses as kind of like a variable. We just do power rule, bring down the -1, subtract 1 from the exponent. The inside we're going to leave intact. We're not ready for it yet until now. In a separate space, we're going to have a designated spot for the inside derivative. Okay, so now we can apply each of these terms separately. What's e to the x become? Times. Okay, so what I guess what I want you to say is that e to the x times 1. I know that the 1 is not going to change anything. You can leave it out if you want, but just want to keep reminding us that yes, we are applying the full rule. It's just that when it's just x, it's going to feel like nothing is happening. Okay, plus e to the negative x becomes times good times -1. Okay, so e to the negative x times -1. Okay. Okay. Any questions with the derivative step so far? I mean, we have the answer. We're just going to do a little bit of cleanup after this step. So outside derivative times inside derivative. Okay, so here's my cleanup stage. I'm going to put the -2 and these terms together. And then the 1 with a negative exponent, I'm going to push it back down to the denominator. You can distribute the -2 through, but you don't have to. And also, we can't cancel anything out, right? And then it's okay that we have some negative exponents left over. Let's just leave it in this form. Okay, questions with 47. Okay, look at 48. Also, numerator denominator. I mean, we could go through quotient rule, but is there a way for us to approach this problem so that we can avoid quotient rule? Yeah, what's nice about this problem that we couldn't do with 47? Okay.
Well, it's also not inside of the parentheses.
Okay. What else?
You can just move 1/2 to in front of both.
Okay. Yes, you guys are all right. I just want to kind of just add to the fact that there's only one term in the denominator. There's only one term in the denominator. I'm always looking to avoid quotient rule, right? Because it just feels a little cleaner. So we can split up in individual fractions. We can push that 1/2 out in front. Basically, the added benefit here is that not only is it one term, but it's just a constant, right? That should make it an easy problem. We should not have to overcomplicate things and go through quotient rule. It's just not worth the effort. So just as a reminder, a problem like this as well, right? If there's only one term in the denominator, I'm always looking to either split up or avoid quotient rule. Okay, so yes, split them up or push it out. Either way, no need for quotient rule, especially if there's such a easy thing to move from the denominator. Okay, so this is a lot less intimidating than this, right? We don't want to look at it in this form. So I can distribute the 1/2 through, and it's going to feel like a much easier problem than what's presented. So now can we just apply the e to the u rule separately? Yeah, the 1/2 is just a coefficient, right? It's just going to tag along. There's no need for product rule, right? So it should feel like an easy rule here, an easy derivative here. Okay, we keep the 1/2. E to the x becomes e, yeah, times 1. You can leave that 1 out if you like. I just want to show you that we are technically the rule is the full rule is being applied. Okay, what about the next one here? Keep the 1/2. Get e to negative x times -1. Okay. Okay. Questions here? Yeah, anytime you want to find the derivative, it's always that first step, right? That first step is the hardest one. Because once you get that first step down, then everything else kind of falls into place. But yeah, the hardest step is deciding what to do at the beginning. Okay, we'll do some cleanup here. This term can't do much. This one, though, I can kind of push that negative in front, kind of merge those two negatives, make it a positive. I can push this e to negative x down to the denominator. Just to make it look a little better here. Okay, how are we so far? Questions? Okay, take a look at 50. Look at how this fraction is constructed. What makes this different than 47 or 48? Yeah, it's not a simple term. So what would you do then? Here, what rule would you use? Yeah, this one, I would say quotient is the best option. Just because of the complexity, it's not easy to move those things around and force it into an easier problem. Students previous periods were saying, well, can we just move this denominator to the top, make it raised to the -1? The answer is yes, you can do that. But I feel like that makes it more complicated because if you bring this up to the top and raise to the -1, not only do you have to do chain rule, you got to involve product rule. Okay, so this is not just a constant. It's just not going to just tag along. So I find that to be more complicated. So in this case, I think quotient rule is going to be the easier path. Okay, you can avoid quotient rule, but I don't think it's easier. Okay, so we'll do quotient rule here. All right, we only want to avoid quotient rule if we feel like the other option is an easier option. And again, the rule that we want to apply, e to the u, is e to the u times u prime. Okay, so let's set up for quotient rule here, 50. Right, and also we can't split up, right? There's too many terms in the denominator. Only when there's one term in the denominator are we going to kind of look to split up. But too many terms in the denominator, we're kind of stuck. Okay, let's start with the numerator, f prime.
E to the 2x.
Okay, e to the 2x times 2. Drag the g function down, no changes. Back to f. Okay, g prime.
2x.
What happens to the 1?
0.
Good, drops out. Denominator squared. Okay, we have our derivative. I'm just going to see if I can clean up the numerator a little bit. Hopefully some like terms will make it look a little bit more presentable. I'll distribute this through. Combine like terms. There's our derivative here. Okay, any questions with 50? So we're looking at these subtle differences between 47, 48, and 50. Kind of recognizing that we don't have to do quotient rule every time. Sometimes there may be easier path to our derivative rule or our derivative steps. Okay, 52. You guys can cross off 52. And what I want to do is I want to re-explore 50, but I want to flip the numerator and denominator. I want it to be e to the 2x plus 1 over e to the 2x. That seems like a minor adjustment or slightly different looking problem. I'd like to explore what we could do here that we couldn't do before. We can still do quotient. We can still do quotient. Is there another option though for 52? Oh, bring it up and go through the product. Yeah, I guess you could do log differentiation. What else though? Okay. What's nice about 52 that was not available to us for 50? Say it again.
Single term.
Good, single term in the denominator, right? So if anytime there's a single term in the denominator, I'm always trying to see what I can do to avoid quotient rule, right? As soon as I see that single term, I'm thinking, okay, I'm gonna avoid quotient rule at all costs. I mean, it's just going to, for the most part, it's going to usually make the problem easier, okay? But if you do quotient rule, it's not wrong, but I want to kind of give us some options here. So single term in the denominator allows us to separate. And if we can separate, we're usually going to be dealing with maybe more terms to deal with, but easier problems, easier terms usually. Okay, so here's my separation. And nice thing about separation is now these terms are independent of each other. I can treat each like a separate problem, and they're not linked together where it's cumbersome to change things, right? Okay, what can I do with this first term? Yeah, becomes what? 1, right? Not 0, right? 1. Is the second term ready, or can we make some adjustments? Move it to the top, okay. And we want to move it up to the top because e to the u does not work in the denominator, right? The rule that we have is designed for the numerator, okay. When you move that that expression to the top, we got to make an adjustment. The exponent is going to change signs. So if you look, these are the same problems, okay, but feels like a much easier problem once we go through our cleanup, right? Okay, so now y prime. First term, 0. Second term, e to the u times u prime. Okay, the 0 goes away. I'm just left with one term. I can maybe push that e down to the denominator. Okay, so hopefully going through those problems, you just feel like you have a little bit more knowledge in terms of numerator and denominator, that you're not stuck with quotient rule every time, that there are certain situations that allow you to avoid quotient rule. Okay. Okay, I want to do one more problem involving this section before we move on to 5.5. You can go to page 18, and let's look at number 58. So next page, 58. Every time that we learn a new derivative rule, we always go back to tangent line equation. That's just like a common thing that that you're going to see over and over again, and it's going to always show up on the AP exam, finding tangent line equations. But all we do is we find the order pair, we find the derivative, and from the derivative we can evaluate the slope, or find the slope, and then finally the point slope form. So 58, order pairs are already provided for us. That's good. We can just find the derivative. To find the derivative, do we have a rule that's easy to apply here? Yeah, a to the u. Everything is set up nicely, right? There's nothing that's getting in the way of this rule. The variables in the numerator. The u is a little messier, but everything is lining up perfectly for our e to the u rule. Okay, y prime. Yeah, 2x minus 2 is fine. Good. Any questions here? We're just following what the rule says. All right, we have the derivative. What else can we do? What should we do next? Not set equal to 0. We do involve the 2, but we want to find f prime of x. So we're going to do what? We're going to insert 2 into the x, right? Insert 2 into the x. So we have our slope formula. If we give it an x value, in return, it'll give us a number, and that number is going to tell us the exact steepness of that curve at that point. Okay, so all we need is the x value. It's a function. No need for the y value. The y value is needed if it's a implicit problem, but you don't see any y's stuck in here. So just the 2, y prime of 2. Okay, so I'm doing a little bit of merging without showing all the steps here. I'm just inserting 2 in for x and just doing some cleanup here. This becomes -4 plus 2 squared, which is 4. This becomes 4 as well. So, okay, -4 plus 4 is 0. What's e to the 0 power? Not 0, good, 1. Okay. Two times 1 is 2. There's our slope. Okay, let's set up 4-point slope form. That's fine, either way. I just, AP exams will accept it without moving that y1 over. So point slope form, y minus 1. Okay, tangent line equation. Any questions? All right, page 19. We're going to start our notes for today, 5.5. All right, does anybody still need 58? Okay, let me write some notes up here. I want to make the connection with the previous rules that we learned. I don't want this to feel like a set of brand new rules. I just want you to think of it as an extension of the rules that we already know. Okay, so I want to put some. We'll do some properties exploration here first. Okay, so if you guys can just jot that down at the top of your page. We learned about how natural log and e to the x are inverses of each other. They have a way of canceling each other out. They're both base e. So we learned that log base e of e to the x is just going to clean up nicely to be just x. E raised to the natural log of x is equal to x. So if I insert an inverse into the original, or the original into its inverse, they're always going to find a way to cancel each other out. Understanding that is helpful because if we're trying to solve for a variable, and if it's stuck inside a function, we can always use the inverse to kind of alleviate that that issue and kind of help cleanly remove the parts that we want to remove. So here's the general rule that I want to get to. The relationship between natural log and e to the x can also be extended to natural log and into log and exponential functions that are of other bases, as long as they're matching. So the general rule is if I have log base b of b to the x, that's going to cancel out to be just x, just like how it would if it was base e. B raised to log base b of x is also x. Does not have to be base e. It can be base 2, it can be base 3, it can be base 5. So let's look at example 1 and see how using the inverse functions can help us clean up and allow for certain things to work. Okay, so the first thing I notice is my variable that I want to solve for is stuck in the exponent spot. I want to find a way to get that exponent to come down, ideally. It's easier to work with a variable if it's not stuck in the exponent. But if I want to bring it down, I have to have logs in place, right? We have properties for logs, but right now it's not part of a log expression. So all the log properties that we learned, power property, product, quotient property, they also hold for logs of other bases. So I'm going to strategically choose log base 3 because I know log base 3 is going to find a way to get this to go away. Whatever I do to one side of the equation, I'm also matching that property on the other side. Now, what do you think we can do here? What's log base 3 of 3 to the x going to turn into?
That's
Just x. Yeah, we strategically chose that so that we can get this to match up. Okay, so now our attention turns to the right side of the equation. How can we get this to hopefully match and cancel out?
quotient property.
Yeah, you can do quotient property. Yep, that works. So quotient property, we have log of a over b can be expanded into log of a minus log of b. That works good. Log of 1 is always 0. Doesn't matter if it's natural log or so. That's just going to go away. Is there a way for us to rewrite this where I can get these two numbers to match? Can I play with 81? Can 81 be represented? Let's think in terms of we want this to happen. We're trying to get the bases to match. Is there a way that I can rewrite 81 in terms of 3? 3 to the what? 4th. 3 to the 4th, right? Okay. 3 squared is 9. 9 times 9 is 81. So that's 4 3s there. Okay. Okay. We have some nice properties here. What's going to happen? This goes away. We're just left with what? 4. There's negative in front, so negative 4, right? Okay, so number 1, we involve logs because we know log properties will allow us to move that exponent that would otherwise be kind of cumbersome to work with. Number 2, though, I want to solve for x, but x is right now it's stuck inside the log base 2. So now I want to find a way to get that log base 2 to go away. I know if I involve the inverse, I can get that to cancel out. So that's exactly what I'm going to do. I'm going to raise both sides with a certain base. What base do I want to choose to get this to work out nicely? Base 2, right? If I can choose base 2, right? I'm strategically choosing something that will work out nicely in my favor. What's going to happen here?
It'll just be X.
Just be X, right? Okay, notice that I'm maintaining balance here. I'm not just doing it to one side without the other side in mind. I'm also raising the other side with 2 as the base. Okay. Let me do a little bit of cleanup. I like to work in terms of positive exponents, so I'm going to push that exponent down to the denominator. What's 2 to the 4th now? 1 over 16. Okay, questions? Okay, so let's talk about the new derivative rule. But I want us to kind of I want us to kind of explore it through the lens of natural log. I don't want you guys to feel like this is a brand new rule. It looks messy, but I want you to feel like it's just an extension from a rule that you already know. If you guys can cross this out, I'll have a different way of presenting it. And also the rule is not quite right, has some typos in there. So let's do this first. Let's start with something that hopefully we recognize and we feel familiar with. What's the rule for natural log of u? What's the derivative rule? Yeah, u prime over u. The fact that it's base e is going to work out nicely. We'd like to think of this as a parent derivative rule. That natural log we know is just right, just base e. We say ln instead of log base e. It's just we use it so often, it just makes it easier to just write it in shorthand form. So we know this rule, right? This is base e. Now, if I have a log that is not base e, right? Base 2, base 3, base 5, base 10. We have a generic rule for that. We call it log base a of u. Okay. Now it's not base e, so there's going to be a little bit of extra thing, something that we have to include as part of this rule. But we're going to basically go through a little bit of a conversion step. We're going to kind of convert it into natural log. And then once it's in natural log territory, we can just do that u prime over u. So basically, I just want you to think of, okay, log base a, natural log, it's basically natural log. There's still that u prime over u, but there's a little bit of extra in front. Okay, so this is what the extra in front I'm talking about. There's a 1 over natural log of a in front. Okay, that's going to kind of do a little bit of conversion. So we like to think of natural log as a parent function, and that log base a is we're going to kind of adjust it into natural log before we apply the rule. So 1 over ln of a times u prime over u. So when you see this rule, I don't want you to feel like, oh, I got to memorize a brand new rule. I want you to think of it as, okay, I know u prime over u, just a little bit of extra in front. Okay, so let's do a practice before we go into some of the problems below. An easier one here. So the first thing you recognize is, okay, I have a log problem. I know it's u prime over u, but it's not base e, so I have to make some adjustment in the beginning. Okay, so y prime equals, let's just follow the rule. What's natural log of a? Natural log of 3. That's going to be the conversion. That's going to kind of put it into a natural log form. And then now it's just going to feel like your natural log derivative, right? U prime over u. What's u prime?
5 minus 6.
Divided by.
5x.
Now your derivative rule will feel a little messier, but it's okay. You can leave it in that messiness. I just asked that maybe we can just get into one fraction, okay? But you don't have to do a whole lot of work once you find the derivative. Okay, so I don't want this rule to feel like something that's brand new. Okay, I just want you to think of it as something, a little bit of added change to my natural log rule, because it's a different base that is not quite quote unquote parent log. Okay, example 3. Find f prime for f of x equals log base 5, cube root of 2x squared plus 7. Let's see if we can rewrite this problem. All the log properties that we used from before can still be used here. Remember, power property, quotient property, expansion properties, all those can still be applied here. It's just that it's different base, but we're still under the log function umbrella. Okay. So imagine this was natural log. Okay. How would you rewrite this problem?
Log 5 would do 2x squared 7 1/3.
To the 1/3. Yep. Radicals, we like to convert to rational exponents. It just feels a little bit more concrete, more familiar. So you approach this problem pretty much the same way that you would if it was a natural log of 2x squared plus 7 to the 1/3. If you see natural log, parentheses to the 1/3, what can we do? 1/3 down, okay. It looks a little more intimidating because it's not natural log, but you have all those properties available still to you. We can't distribute the log 5 through, right? This is stuck. However, we're just going to apply our derivative rule. Just think, all right, I just u prime over u with a little extra in front. Okay, how would you start this derivative? What would you put down first? Yeah, it's a coefficient, right? It's just going to tag along to the derivative. We just have to put it down. Okay, what's next? Convert to a log to a natural log. So 1 over ln of 5. So it's a little bit of extra step in front. Now everything should look familiar, right? U prime over u. Okay, u prime. It looks a little messier, but all I'm going to ask is you get it into one fraction and just leave it. Okay, example 4. Imagine this was natural log. Natural log of 5x cubed over x squared minus 3x cubed. What would come to mind? Quotient property, right? So any natural log property also applies for logs of other bases. Okay, so we're going to expand this out. Now, we don't see a base that's written here. Do you guys know what that base is if it's hidden? Base 10. The reason why base 10 and base E are the most commonly used bases, so we have kind of special shorthand form for them. ln for log base E and log for base 10. But for right now, I think it's helpful if you just put a 10 as you write them down. It kind of helps you with the derivative step because you know what your A value is going to be. Okay. So here's my expansion. Sorry, I forgot to put it down. Okay. Log of A minus log of B. I'm going to put that 10 there. So visually, it kind of helps. Okay. Is there anything else that we can do to maybe expand before we explore derivatives? Which one? Second one. Can we do it with the first one?
No.
Yeah, well, and also there's a 5 there, okay? And also, you're looking at this going, I don't want to expand. This is already easy. This is an easy U value, right? This is not as easy. So you only want to expand as far as you feel like the expansion will make the U value easier to work with. Okay, if the U value is already manageable, then it's not worth the trouble to expand. And now we can just apply the rule, right? 1 over ln of A times U prime over U. Okay, we'll pick this up tomorrow. You guys have homework from 5.4. And I'll send out a reminder of that and the test review help session schedule.